Hello, everyone. Welcome to Physics 205. So this lecture, I want to talk about something called uniform circular motion. And then eventually we'll get into the topics of centripetal acceleration and centripetal force. Now, uniform circular motion means an object is traveling in a circle and it's traveling at a constant speed. Okay, so I'm going to start by drawing a picture here. Let's say we have some object, it's traveling in a circle, so like this. Here's the center of the circle. And at some instant in time, it has a velocity, say, directed to the left here. So this is, say, v1. And then let's say a short time later, right, it's traveling around a circle, it has a velocity like this. So the velocity is always going to be tangent to the path. And because it's traveling at a constant speed, the length of that velocity vector is going to be the same. So the length of v2 is the same as the length of v1. But notice that the direction is different, okay? So here, let me write down what I have so far. So we have an object traveling at a constant speed in a circular path. Okay, so that's what it means by uniform circular motion. Now, remember the formula for the acceleration. So remember the average acceleration, which is really a vector, is the change in velocity divided by the change in time. And I can write this change, in this case, if I actually want to calculate this, I could write this as v2 minus v1. That would be the change in velocity divided by the change in time. Now you might think, well, wait a second. In this example, this object is moving at a constant speed, right? So why would it have an acceleration? Because almost all the other examples we did were one-dimensional motion. And if the speed is changing, there's certainly an acceleration. But if speed doesn't change in a one-dimensional motion, then there's no acceleration. But you have to be careful. Acceleration is the change in velocity over the change in time. And since velocity is really a vector, that means if the magnitude of the vector changes, so the magnitude of velocity changes, you can have an acceleration. Or if the direction of the velocity vector changes, like in this case, then we also have an acceleration, or both. You could have change in direction and change in magnitude. In this case, we just have a change in direction, but no change in magnitude because the speed is the same as constant. So in this case, we actually do have an acceleration. We don't see this, we haven't seen this yet when we have constant speed because we just had one-dimensional motion, right? So we didn't really have a change in the direction of the velocity. But since now this object is moving around the circle, the direction of the velocity is changing. So I can get an idea of the direction of this acceleration by calculating this numerator here, by calculating the change in velocity. Because remember, the velocity is the vector, right? So change in velocity is a vector. Delta t is just a scalar. It has no direction. So the direction of the acceleration comes from the direction of the change in velocity. Like that's a key point. The direction of the acceleration is going to be given by the direction of this change in velocity, which is really v2 minus v1. So here, let's actually draw this out here. So remember, to subtract vectors, I can start by taking v2 and I can add the opposite of v1. Right? Remember, v2 minus v1 is the same as v2 plus negative v1. So if I draw v2, v2 is something like this. And then negative v1. So if this is v1, right, pointing to the left here, then remember negative v1 is going to be a vector of the same length, but pointing to the right. So if I add negative v1 to v2, I put the tail of negative v1 at the tip of v2. So like this. So this is really negative v1. So I'm adding tip to tail, right? I have v2 plus negative v1. And that's going to give me the resultant, which in this case is delta V, which is going to point in this direction. I'll do it in red. So this is my delta V. That is V2 plus minus V1, or V2 minus V1. So since my change in velocity points in that direction, that means the acceleration is also going to point in that direction. And it turns out in this case, that direction is towards the center of the circle here. So that acceleration points in the same direction as the change in velocity towards the center of the circle. So this object does undergo an acceleration. Let me write that down here. So the object undergoes an acceleration. The direction of the acceleration is towards the center of the circle. Okay, so we know the direction. Now, what is the magnitude of this acceleration? Well, the magnitude is given by this formula. So it's A, and then I'm going to use the subscript C. This is really what we call the centripetal acceleration. So let me write that in here. Centripetal means like center seeking. Centripetal acceleration. So the direction of the centripetal acceleration is towards the center of the circle, and the magnitude is given by the speed squared, right? The magnitude of velocity, which is the speed squared, divided by the radius. And it's going to have the same usual units of acceleration. It's going to be in meters per second squared. Okay. On the next page, will derive where this comes from, where this magnitude, where I got that magnitude, where that comes from. But for now, let's just list it as V squared over R. Okay. So, and again, V is the speed, right? That tangential speed. And R is just the radius. So R is the radius of that circle. Okay, so if you know those two variables, then you can calculate the magnitude of that centripetal acceleration. All right, there's another way that we can actually represent the centripetal acceleration, and it's using something called the angular speed. So if I have, let me draw a circle again. Let's say the object is at this instant right here, moving with some velocity. So this is V. Then the angular speed, which we call omega, is basically how many radians of angle it's sweeping out per time. So omega is in radians per second. See, so omega basically is the change in the angular position divided by change in time, right? It's how many radians it's sweeping out per time. So if that's omega, the V we have the speed, and let's say the radius is R, then it turns out that V, that velocity, can be written as omega times R. So let's check units here. Well, omega is in radians per second. R is in meters. If I multiply those units together, you have to remember radians really, it's just to remind you that the angles in radians is not really a unit, that it's really unitless because it's a ratio, right? Remember, here, let me do this for a second over here. If we have an angle here, say theta, and this is r, and let's say we know this arc length, the length along the circle here, we'll call s, then radians are defined, if that angle's in radians, it's defined to be the length of that arc, so the arc length divided by the radius. So if one of those is say in meters, the other one's in meters, they cancel, right? So really there's no units when we talk about radians. So just to remind us that we're in radians. Also, you should remember that a full circle, if you go all the way around, right, that's 360 degrees. But in terms of radians, that's equal to 2 pi radians. So a full circle all the way around, that angle is going to be 2 pi radians. So if we know that 360 degrees is equal to 2 pi radians, that we can use as a unit conversion factor. In fact, usually what people do is they divide this by 2. And they say 180 degrees is equal to pi radians. Okay, so you can use that if you know your angle in degrees, then you can always convert to radians. All right, so if we go back to our picture here, this object is rotating at a certain number of radians per second, right? Instead of degrees per second, it's in radians per second, right? So we call that sort of an angular speed. So omega is really just the angular speed. This is the angular speed. So if I want the linear speed, if I want the velocity here, really the magnitude of the velocity, so that speed, it's simply equal to the angular speed times the radius, right? So that's what I have written here. So v is omega times r. So the point I'm trying to make, remember earlier, we just said that the centripetal acceleration is equal to v squared over r. But we just said v, if I want to write it in terms of the angular speed, I can write that as omega times r. So I could substitute this in. So this v here, I could plug in, and I'm going to get omega r all squared divided by r. But that is equal to omega r squared, oh, sorry, omega squared r squared divided by r. One of the r's is going to cancel. So another way of writing the centripetal acceleration, instead of v squared over r, I could also write it as omega squared times r, right? They're both equivalent, and it really depends on whether you're given the angular speed omega or whether you're given the tangential speed, the v. This depends on what information you're given. And of course, this has the same units, meters per second squared. Okay, I said I would discuss how we actually came up with this equation here, right? How that magnitude of the centripetal acceleration is v squared over r. So let me do that on the next page. All right, so first thing, let's assume that this object has undergone a small angular displacement, which I can call delta theta. This is the radius, and it's moved a small amount, right? It's moved like a small arc length, which I'll call delta s. Now, in the same time, the velocity vector has also moved a small amount. So let me draw this again. But now I'm going to draw the velocity vector. So originally the velocity vector is like this. This is like v1. And then at this instant, it's tangential. It's like this. This is like v2. Okay, and again, this is delta theta. If I put the tails of those two velocity vectors together, so I'll draw v1 like that, and if I put the tail of v2 at the tail of v1, it looks like this. Remember, it's constant speed, right? So they have the same length. And then this distance right here is really delta v. Okay, that's really v2 minus v1. If you did that actual subtraction, you'd find that that length is delta v. This is delta theta here. Okay, so these two triangles, because they have the same angle, right? And then these two angles will also be the same. They're different sizes, but they have the same angle. These are called similar triangles. So these are similar triangles. You can think of similar triangles as triangles that have the same shape but different sizes. Yeah, actually, let me draw again so to show that they're similar. So this was the first one, right? Where I have delta theta r and then delta s, and then this is the second one where I have delta theta. Then this is v. Right, v1 and v2 have the same magnitude. I'm going to call it v. And then this is delta v, the change in velocity. So because these two triangles are similar, we know that the ratio of the corresponding sides are proportional, right? This comes from like an introductory algebra class or introductory geometry class. So if you have two similar triangles, then the ratio of their corresponding sides are proportional. By the way, because this is such a small angle here, oops, let me go back. Because this is such a small angle, delta theta, you can think of these arc lengths as being just lines. So you can think of these as being straight. So that actually looks like two triangles. Okay, so they're similar triangles, so the ratio of the corresponding sides is proportional. So what does that mean? It means if I take the ratio of, say, delta S over, well, the corresponding side to the second triangle is delta V, right? So delta S divided by delta V must equal, I go back to the first triangle, say R over its corresponding side, which is V. So that equals R over V. And then I'm going to rearrange this. I'm going to solve this for delta V. So to do that, right, you can multiply both sides by, I guess I'll multiply both sides by the lowest common denominator, which is delta V times V. Or you could just actually, let's just cross multiply in this case. So I'm going to cross multiply. So multiply that way and that way, right? So upper left times bottom right. So I have delta S times V equals bottom left delta V times upper right R. And then to get delta V, I'm going to divide both sides by R. Okay, so I have delta V is equal to, right, these cancel, V times delta S over R. Okay, now I'm going to divide both sides of the equation, and I can do this, right, as long as I do it to both sides, by delta T. Or another way of saying this is I can multiply both sides by 1 over delta T, which is the same as dividing both sides by delta T, right? Either way. So if I do that on the left-hand side, I'm going to get delta V over delta T. That's the acceleration, right? That's the magnitude of acceleration. That's what we want. On the right-hand side, I'm going to stick the R under the V and then times in delta S over delta T. But this term right here, right? Remember, this is the arc length, the small change in arc length divided by the time here. This is just the velocity. this is another way of writing v. That's just the speed, right? It's the magnitude of the velocity, which is the speed. So this term, which is really our a, is equal to now v times v, which is v squared, divided by r. So that's where it comes from. It's a little complicated. You had to know a little bit of geometry to get this. By the way, it's actually much easier to derive this if you use calculus, but since this class doesn't use calculus, we had to do it geometrically, right? Don't worry too much about this derivation. The important thing is that you have this, and we can use this magnitude of the centripetal acceleration as v squared over r. Or if you want to write it in terms of the angular speed omega, you can write it as omega squared times r, right? As long as you remember that, that's fine. Don't really worry about this derivation. Okay, let's do some examples here. So this first example, it says a 1 kilogram ball is tied to a string of length 1.5 meters. It's swung around your head such that the ball is moving in a horizontal plane, and it has a speed of 3 meters per second. What is the tension in the string? Okay, so let's say this is the center of the circle, right, that you're spinning the ball around. It has a radius. I'll just call it r for now. Here's the ball. It has a particular mass. And let's say it's moving at this instant with a velocity in this direction. So we know that speed v is going to be 3 meters per second. And what we want to calculate is we want to calculate the tension in the string here, which is going to be the force, right, in the string here towards the center. Okay, we know that this ball is going to be moving in a circle, right? So it's going to be moving something like this. Moving in a circle. So because it's moving in a circle, it's going to have a centripetal acceleration. It's going to have an acceleration towards the center. Now, due to Newton's second law, if there's an acceleration, there must be a net force, right? Because remember, Newton's second law says that the sum of the forces is equal to mass times acceleration. Really, these are vectors. In our case, we want to look at what's going on just in what's called the radial direction, which is like towards the center here. So if I draw, let me do it this way. So towards the center, yeah, I'll draw a little coordinate system here. This is like, I'll call it the plus r direction. This is the radial direction. So when I apply Newton's second law, I just want to break it up to the forces acting in the radial direction. So I'm going to have the sum of the forces in the r direction is got to equal m times the acceleration in the r direction. But what's the acceleration in the r direction? That's our centripetal acceleration. That's what we called AC, right? That's our centripetal acceleration. Well, in this case, what are the forces acting in that radial direction towards the center? Well, we only have one of them, right? It's the tension. So the sum of the forces in the radial direction are going to be just the tension. That's it. There's nothing else acting in the radial direction. And that's got to equal m. And then for the centripetal acceleration, remember, we can either use v squared over r or omega squared r. But since we're given v, we're given r, let's use the v squared over r. So that's the equation that will allow us to figure out the tension. And again, all we did was use Newton's second law, right? The net force, sum of the forces equals mass times acceleration. But we applied Newton's second law just to that radial direction towards the center of the circle. So we found all the components, right, of the force, and there's only one force in the radial direction. And that's got to equal the mass times acceleration in the radial direction, which is that centripetal acceleration that we just found. So now that I have all this information, I can solve this problem here. So tension is going to be the mass, which we know is 1, right, kilogram, times the velocity is 3 meters per second squared, divided by the radius, which is 1.5 meters. And if you work that out, you're going to find that this is 6 newtons. So in general, the force that is acting in that radial direction is called the centripetal force. So in this case, this tension that we just found is really the centripetal force. So this tension is the centripetal force, right? It's the force that acts in the radial direction. Okay, so when we say sum of the forces in the radial direction equals m times v squared over r, then this left-hand term here, whatever that net force is, the sum of the forces, this is the centripetal force. It's not special, right? Because it's just due to the tension in the string. There's no special force. It's just the fact that we give it a name because it's acting in the radial direction. So that centripetal force is acting in the radial direction. Okay, here's another example. You're told that a car travels at a constant speed of 13.4 meters per second on a level circular turn of radius 50 meters. What is the minimum coefficient of static friction, µs? So this, when they say coefficient of static friction here, they mean µs. So this is going to be µs. Let me write it here. Between the tires and the road that will allow the car to make the turn without sliding. Okay, so first of all, just to get an idea of what's going on, let's draw a picture here. So I'm going to draw a picture like looking from above first. So I'll say from above. So we have this car, right? It's traveling around a circular path like this. So this is just like the instant, let's say it's right on the left-hand side at the instant. And we know that this radius, so that's the center of the circle, is r, which is going to be 50.0 meters. And we also know the velocity, let's say it's moving counterclockwise. So at the instant, it has a velocity of speed, which is straight down of 13.4 meters per second. Okay, and so this car is going to travel around the circle at that speed. Now, in order to do that, right, we know that this car is going to have a centripetal acceleration towards the center. So there must be some centripetal force acting towards the center to keep it moving in a circle. Right? If it's moving in a circle, that means there's an acceleration towards the center. So there must be some force, which we call the centripetal force, acting towards the center to keep it moving in that circle. Now, what causes that force? Let's draw this picture again, but looking like from the front. So if we're over here somewhere and we're looking at it from the front, so it'll look something like this. So here's the car. Right here are the tires. This is going to be the radius. So this is R. It has several forces acting on it, right? So it has, this is the road here. The forces acting on it are the weight of the car, right? The gravitational force, which acts straight down. We have the normal force that the road exerts on the tires straight up. So normal force. And then what is the force that's acting towards the center that's keeping it moving in the circle? What's causing that centripetal force? That's got to be the friction, right? The friction from the road acting on the tires towards the center, like this. And because we want to know the minimum coefficient of static friction between the tires and the road that will allow the car to make the turn without sliding, So we want to know, like, basically, what is the maximum static frictional force that we can apply to the car here so it keeps moving in a circle. So when we calculate that static frictional force, Fs, it's really going to be the Fs max, right? We want it to be the maximum. What's the maximum static frictional force we can apply to the car so it continues to move in the circle at that speed, at that radius? Does that make sense? So this max static frictional force, that is what allows this car to move in a circle, right? That's the same as the centripetal force acting towards the center here that allows it to move in a circle. Okay, so how do we find this? Well, let's do some, let's apply Newton's second law. First thing, we know that Fs max remember, the model of it is going to be mu s times n. So if I can figure out n and an Fs max, then I can calculate mu s because we want to figure out what the mu s is. Okay, so we know Fs max is mu s times n. Let's apply Newton's second law. I'm going to do the y direction first. Okay, so looking at, this is based on my free body diagram. Let's look at the sum of the forces in the y direction. That has to equal ma y. So I have the y component of the normal force plus the y component of Fs max plus the y component of the weight. Remember, I'm finding all the components. That's got to equal may. So the y component of normal force. Here's my coordinate system here. So I'm thinking of the x as being like in a radial direction and the y being vertical. So what vectors, these are all really vectors, right? Which of them are acting in the y direction? Well, the normal force is, in fact, all of it is in the positive y direction. So the y component of n is going to be just all of n, right? So ny is just all of n because it's acting straight up. If you want, you can draw like a little coordinate system here. This is the x, and this is the y. So that normal force is acting all in a positive y direction, right? So it's all of n. What about the max static frictional force? How much of that vector is in the y direction? None of it, right? It's all in the positive x direction. So that's going to be 0. And then finally, how much of, this is 0. How much of the weight is in the y direction? All of it, and it's negative, right? So this is going to be minus mg. And then one of the constraints here is that this car is not leaving the ground, right? It's not moving in the y direction at all. So the acceleration in the y direction is 0. So this term is 0, which means that right-hand side is going to be 0. So basically, this just tells us again that in this simple case, the normal force is simply equal to the weight of that car, right? So normal force is equal to mg. Now let's do Newton's second law applied to the x direction. So now I have sum of the forces in the x equals max. So now I want the x component of the normal force plus the x component of the max static frictional force plus the x component of the weight. That's got to equal max. Okay, but the x component of the acceleration is the centripetal acceleration, right? Because that's the acceleration that's acting towards the center. The x direction is like the radial direction towards the center. So ax is really the same as a centripetal. So I'll write that here. So ax is equal to a centripetal. And then we can either write that as omega squared r or v squared over r. We're going to use v squared over r. So ax is really the same as v squared over r. So if I fill everything in here, what is the x component of the normal force? How much of this normal force is in the x direction? None of it, right? It's all in the positive y. So this is 0. How much of that max static frictional force is acting in the x direction? Well, it's acting to the right, which is the positive, right, radially, which is the positive x direction. So all of it is in the positive x direction. So the x component is the entire Fs max. And then how much of the weight is in the x direction? None of it. And this is equal to max, but remember ax is the same as ac. So this is going to be v squared over r. Now, we just said earlier that Fs max here is mu Sn. So if I want, I could write on the left-hand side, I could write mu Sn is equal to mv squared over r. And we found earlier here that N, the normal force, is just the weight. So I could fill that in. So this is mg, right? N is mg. I'm just substituting in, which is mv squared over r. And then finally, I can simplify this a little bit, right? I can cancel the masses, and then I could divide both sides by g. So I'm going to solve this for mu s, right? So divide by g, divide that by g. So mu s here is going to be v squared over rg, right? That g will just end up in the denominator. By the way, if you want to prove that here, you can think of this as you have a fraction, right? V squared divided by r, and you want to divide that by g, which you can think of as g over 1. And remember how to divide fractions? You take the first fraction, v squared over r, and you multiply by the reciprocal of the second. So that g is just going to end up in the denominator. And now we have everything that we want, right? The whole goal was to figure out what that mu s was. What is the coefficient of static friction between the road and the tires that allows that car to move in a circular path? So I can plug in now. So my v is my magnitude of velocity, which is my speed. That was 13.4. Let's square that. The radius was 50. And then g, of course, is 9.8. And if you work that out, you're going to find that this is 0.37. Remember, there's no units, right, for the mu's. So the coefficient of static friction between the road and the tire is around 0.37, okay? And all we did for this problem is we used Newton's second law, but we used it in the radial direction, which in this case we call the x direction. Right, so we applied Newton's second law to the radial direction, which in this case we wrote it as the x direction. Okay, let's do one more problem here. So in this problem, you're told part of riding a bicycle involves leaning at the correct angle when making a turn, as seen in the figure below. I'll show it to you in a second. To be stable, the force exerted by the ground must be on a line going through the center of gravity, okay? The force on the bicycle wheel, so the force that the ground exerts on the bicycle wheel, can be resolved into two perpendicular components. One component is simply the static frictional force, right, which is parallel to the road. And that is the force that must supply, that's really the centripetal force, right, that allows the cycle to turn in a circle. And then the other component of that ground force is going to be the normal force, right? It's the vertical component, which is the normal force. And that must equal the system's weight. We'll see that in a second. So what we want to do here is we want to show that the angle theta, as defined in the figure, I'll show the figure in a second, is related to the speed v and the radius of curvature by that equation. Theta is the inverse tangent of v squared over rg. And then once we have that, then we want to actually calculate theta for a particular situation where the velocity, the speed is 12.0 meters per second, and then the radius of turn is 30.0 meters, right? So those are like values for, say, a race or something. The bicycle is traveling in a circle. Okay, so it sounds confusing. Let's look at the picture here. So here's the picture. So this is the ground. It's like a ground reaction force, right? This is the force that the ground exerts on the bicycle tire. And notice that they said in order for everything to remain stable, it goes through the center of gravity of the person. Let's say the center of gravity of the person's right there. So that's where the weight of the person acts, right? The weight of the person's acting down. So on this bike and this person, actually, this weight right here is really the weight of the person and the bicycle. They're combining them together. So let's say the center of gravity is here and the weight is acting down. And this force, this ground force, is going through the center of gravity. And it has two components. If you project this down to the ground, it has this component, which is parallel to the ground. That is going to be the um, the static frictional force, and it's really the centripetal force that allows this cyclist to go in a circle. Right? If you're looking from above, this cyclist, if I look from above, the cyclist is at an angle, but it's traveling in a circular path, just like that car was in the previous example, right? It's traveling in a circular path, where this is like the radius and this is the speed, v. Okay, so that frictional force here is what allows that cyclist to travel in a circle, right? That is really the centripetal force. And then the other component of that force, that ground force, if I project onto the y-axis, is the normal force, right? That's the force that the ground exerts on the bicycle tire perpendicular to the ground, right? Perpendicular to the surface. And we're going to find later that's just equal to the weight of the person in the bike. Okay, so I'm going to draw this again. Let me go to a new page here. Actually, I'll just go back to this page. Actually, I need more room. Let me go to a new page. Okay, so here is the drawing again. Here's like the bike tire. Right here is the person. And then they have their weight. So this is really, again, the weight of the person and the bike acting straight down. And then we have the centripetal force, which is really the static frictional force. I'll just call it, I'll call it FC for like centripetal force. It's really going to be the static frictional force though, acting towards the center. This is sort of the radius here. So this would be like R. And then the other component of that force is the normal force, which is acting up like this. So centripetal force towards the center and normal force. And again, these two combine to make this ground force, this total force that goes straight through the center of mass. So this is like the force F. So we basically find the components of that force F. The centripetal force and then the normal force. Okay, so let me apply, and then the angle, the angle that we want to find is actually this angle. They defined it this way as theta here. So relative to the vertical. So like how much the bike is leaning relative to the vertical is that angle theta. All right, so first of all, let me create a coordinate system. Let's say X is just to the right, and then Y is vertical. So actually in this case, that's going to be like the rate. So this X direction is like the radial direction, and then Y is like vertical. And now let me apply Newton's second law. I'll start with the Y direction. So I have sum of the forces in the Y is equal to MAY. So I want the Y component of the normal force plus the Y component of that centripetal force, which is really the frictional force, right? Static frictional force, plus the Y component of the weight. That's going to equal MAY. But again, in this nice case, this is nice. We don't have to do a lot of trig, right, with the examples, because these vectors are pointing right along the axes that of our coordinate system that we set up. So what is the Y component of normal force? Well, that normal force, all of it is acting in the positive Y direction. So this is all of N. What's the Y component of the centripetal force here, this static frictional force, well, none of it is acting in the y direction, so that's 0. And then what's the y component of the weight? So how much of that weight vector is acting in the y direction? All of it is acting in the y, and it's negative, right? So this is going to be minus, and we know that the weight is just minus mg. And then, again, we have another constraint. This bike is not leaving the ground in the y direction, so the acceleration in the y direction is 0. So again, this just tells us that the normal force is equal to the weight of the person in the bike, right? The total weight of the person in the bike. Okay, what about the x direction? So now I have sum of the forces in the x direction equals max. Well, just like before, because the x direction is the radial direction, that ax is the same as a centripetal, which we're going to write as v squared over r. So if I want the sum of the forces in the x, that means I want the x component of the normal force plus the x component of the centripetal force, right, which is that static frictional force, plus the x component of the weight. That's got to equal mv squared over r, because ax is ac, which is v squared over r. The normal force and the x component, there is no, right? It's all in the y. So there's no a component of that vector that's in the x direction. For the centripetal force, yes, all of it is acting in the x direction. So that's all of Fc. And then for the weight in the x direction, that's 0. And that's going to equal mv squared over r. So I know that F centripetal is mv squared over r. Okay, now how am I going to find the angle? Because remember, the ultimate question was to figure out that angle. If we go back to the question here, we want to show that theta is equal to that equation, inverse tangent of v squared over rg. Well, to get that angle, we have to do a little bit of trigonometry now. I'm going to draw this. So this is my F, right? My force. And because I want this angle, I'm going to draw it like this. This is really the normal force, right? That length of that triangle. This was FC, right? If you look back at the picture here, FC is here, but it's the same as this length, right? And then we have the length, that force that's going through the center of gravity, the magnitude of that total force is just F. So that's like the total ground reaction force, which is split up into the normal force and the centripetal force. Okay, so something like that. So if you think about this, right, if you use our trig, tan of theta, so tan of theta is going to be what? Well, remember SOHCAHTOA? TOA. So TOA says that tangent is the length of the opposite side, which is FC, divided by the adjacent side, which is the normal force in this case. So it's FC divided by N. Well, FC here, we just found was mv squared over r. And N we found is mg. So if I divide these two fractions, again, if you want, you can think of this as mg over 1. Remember, this is the same as the first fraction times the reciprocal of the second fraction. The m's cancel, and I'm going to get v squared, right, times 1, which is v squared. And then in the denominator, I have r times g, which is just rg. So that means that tan of theta is going to equal v squared over rg. And then how do I find the angle theta? I have to take the inverse tangent, right, of both sides. So if I do inverse tangent of tan of theta, that gives me theta. And then whatever I do to one side, I have to do to the other side. So this is just theta, right? Inverse tan of tan, it undoes it. So you just get the argument theta. That's got to be inverse tan of v squared over rg. And that's what we're asked to show, right? So we showed that that's the correct formula. Okay, and then they want, what was the second question? Oh, I think just to solve it for particular values, right? Yeah. So calculate the angle theta when the speed is 12 meters per second and the radius is 30 meters. Okay, so if I go back to this picture here, this radius is now going to be 30 meters. It's hard to see from the, like, if we look from above again, then it's the V here is the speed, and that speed is the 12, right? 12.0 meters per second that they're moving around this circle in. And this radius is the 30 meters. So I simply just plug in, right? We derive the formula for theta. So now I can say theta is equal to inverse tangent of 12.0 squared. So I'm going to square that, divided by, and then the radius is 30, and g, of course, is 9.8. So be careful, right? Do that in your calculator carefully. Remember, we want the inverse tangent of that, and then we're going to get an angle in degrees. Make sure your calculator's in degrees of 26.1 degrees. So what this is saying is that that bike is leaning at an angle of 26.1 degrees, given that speed and that radius. So this angle right here would be 26.1 degrees. So it's leaning like 26.1 degrees relative to the vertical. Okay. But again, this is really a problem that involved a centripetal force, which is that static frictional force acting towards the center, and centripetal acceleration, right? It was a uniform circular motion problem. All right, great. Thanks.